Hi everyone. By now, most people in the AI space have seen impressive demos of music generation like Suno, and here we refer to text to music, lyrics to audio, full songs from prompts. But very few people actually understand how these systems are built, not at the architectural level and definitely not at the code level. Today, I want to do something different. HeartMuLa just came out a few days ago, and it's a fully open source paper which comes with the code and the demo. And I want to walk through the actual model architecture and then go straight into the real production code that runs the system. Let me scroll to the second figure. Here we see that it gets really close to the state-of-the-art models within this space. But I want to start from the heart for you to better understand what's happening behind. So we go with HeartCodec, which is a neural audio codec, similar in spirit to encoder or soundstream, if you are familiar with those, but optimized for music semantics, not just waveform reconstruction. And on the left side, you see three encoders working in parallel. MuEncoder, which captures musical structure, WaveLM captures acoustic and timbral information, Whisper captures speech, line, semantic features, and the key idea here is semantic richness. They are not compressing raw audio, they are compressing meaningful musical representation. So all these goes into our compressor, and this is what's in the middle. Instead of standard vector quantization alone, they use this ultra low frame rate bottleneck combined with query based extraction. And this performs quite well because it means fewer tokens per second, which is critical if you want an autoregressive model to scale to minutes of music. And on the right, there is the decoder side. We do reconstruct the audio using flow matching, which improves stability and fidelity, and a structured quantization decoder, which maps tokens back to waveform. The output is high fidelity audio at 48 kilohertz, which already tells you this system is meant for production quality generation, not toy demos. Moving on, we step into the architecture of HeartMuLa somewhere down here. Okay, let me slightly zoom out. And as we understand how audio becomes tokens, we can move to this. And this is what I was saying before. HeartMuLa is not just a music model, it's a multimodal language model that operates over text tokens, continuous embeddings, and audio tokens at the same time. We do have different input modalities and text tokenizer for description and lyrics, audio encoder for reference music, hard codec tokenizer for target music during training. All of these get merged into a shared token space. Then we also have the global backbone, which is a transformer that learns long range structure. And here I'm referring to song level coherence, progression, repetition, like verse, chorus, bridge, chorus. And here is where musical form lives. And above, we do have the local decoder, and this handles fine grained timing, rhythm, articulation, microstructure, the separation between global planning and the local realization is one of the most important design decisions in modern generative audio. And at the top, we do have the detokenizer. Finally, generated audio tokens are sent back through HeartCodec to become real waveforms. That closes the loop: text, tokens, music, audio. So that means we can transition to GitHub. I hope you got everything right. If not, feel free to ask me in the comments. And also don't forget to subscribe if you're not already subscribed. And here it's, so that's the theory. Let's see how much of this actually survives contact with real code. Spoiler, most of it does, and that's what makes this repo actually interesting. We do have a few examples, and in the source, in the heartlib, we have configuration for both HeartCodec and HeartMuLa, but within the pipeline, if we go in the music generation Python file, the repo is cleanly structured. Okay, yeah, here we can see function as well, but HeartCodec and everything, the first function we see at the top is resolve paths, which enforces strict assumptions. No silent failures. If a checkpoint tokenizer or config is missing, the pipeline crashes early. That's good engineering. We do have device and lazy loading with resolved devices. Notice how they silently support separate devices for HeartMuLa and HeartCodec. This matters because HeartMuLa is a memory heavy. We do have a transformer behind, don't forget, and HeartCodec is compute heavy. That's because it's an audio decoding. They also support lazy loading, unloading models between steps to free VRAM. This is not academic code. It's written with people who have hit GPU limits. I know how it feels like. And I was telling you before about the config, which defines token boundaries, and POS EOS for audio. This allows text and audio generation to coexist in the same autoregressive loop without ambiguity. The preprocessing part, there is this preprocess function. Can we go down here? Okay, GitHub is really cool. This is where prompts become model-ready tensors, tags are wrapped in tag tokens, lyrics are tokenized separately. Everything is concatenated into a parallel token matrix, not a flat sequence. This allows the model to attend across modalities cleanly. Let me go back to all of them. What else we have here? So there is this autoregressive frame generation as well. Generation happens frame by frame. Each step produces audio tokens, not waveforms. Also, there is this CFG, which stands for Classifier Free Guidance, is implemented directly in token space, not post hoc. That's more stable and more controllable. And we should also have the tokenization here. Yeah, the post process. And finally, tokens are passed to a hard codec to the tokenized method. Output is saved at 48 kilohertz, as I already told you. Aligns perfectly with what we saw in the paper. And from paper, we go into the architecture and code nothing of. So that's what I like about HeartMuLa. Is not just the results, is the consistency. The paper makes architectural promises, the code actually keeps them. If you're serious about generative audio, this is one of the cleanest references implementation out here in 2026. I'll link the paper, the repo, and my own analysis below. I've done one on Medium, and if you want more content like this, deep technical, please let me know in the comments down below. And thank you for supporting me. Have a nice day or night.